Hello. In this video, we're going to look at trig derivatives, which is section 3.3 in the textbook. Now, rule 1 is we're going to find the derivative of sine x, which hopefully you tried in the previous video as a bit of a problem-solving exercise. If you're able to get the rule, that's awesome. If not, let's go ahead and see how you might do the proof for this. Now, again, we think the derivative of this is going to be cos x. That's our prediction. And we'll see if that's indeed correct. Now we can jump right into the limit definition. We have the limit h approaches 0, sine x plus h minus sine of x over h. Now remember, we need to somehow factor and cancel things and work on it. And to do that, we need to find a way to expand this. And the rule, of course, is a trig identity. To expand this, we use a trig identity. So the trig identity we have here is sine of a plus b. So this will be equal to sine of a, which is x, so sine x, cos of b, so cos h, plus cos x sine h minus sine x all over h. Now if you notice, this term and this term both have a sine x, so we're going to put them side by side. And in fact, we'll break off the other term and just put it as its own fraction. So this will give us the limit h approaches 0 of sine x cos h minus sine x over h plus cos x sine h over h. So we're just going to go ahead and break it off. Remember, that's the thing you can do with fractions. You can put them both over h because they have now the same denominator. You could combine this to be addition, and we'd be right back where we started. Now let's look at that sine x, which we have in common here, and let's factor that out. So that will give us the limit h approaches 0 of sine x cos h minus 1 over h plus cos x sine h over h. All right, well, let's think about our limit laws. We have the limit of addition, or the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. So we can split this all up and look at each limit individually. So limit h approaches 0 of sine x, limit h approaches 0 of cos h minus 1 over h, limit h approaches 0 of cos x, limit h approaches 0 of sine h over h. Now the limit of sine x here is going to be just sine x, because sine x is technically a constant with respect to h. Cos h minus 1 over h is a special limit. We know that that gives us 0. Limit of cos x is just cos x, because again it's a constant with respect to h. And sine h over h, that's the same thing as sine theta over theta. That's another special limit, and we know that one is 1. So 0 times sine x is 0, cos x times 1 is just cos x. And there we go. We have the proof of our derivative. And so our first rule here for trig is that the derivative of sine x is cos x. Now for rule 2, we want to find the derivative of cos x. And it might be natural to assume that maybe it's back to sine x. So again, go ahead and try to prove this. I encourage you, pause the video here and go through the same steps we just did. Do the cos of x plus h minus cos x and see if you can find out the derivative of cos x. All right, assuming you gave it a try, you should have something like this. Cos x plus h minus cos x over h. And again, we need right here another trig identity. In this case, the trig identity we should use is cos of a plus b, which is cos a cos b minus sine a sine b. So this gives us limit h approaches 0, cos x cos h minus sine x sine h minus cos x all over h. All right, well, we notice again that there's a cos x and a cos x. We can write those side by side, so we can do a little bit of factoring. Get ready to factor them. So limit h approaches 0, cos x, cos h, minus cos x over h, minus sine x, sine h over h. Next up, we go ahead and factor those cos x. So limit h approaches 0, cos x, cos h minus 1 over h, minus sine x, sine h over h. Again, we know our limit laws. We can go ahead and apply limits to each one of these. So we're going to have limit h approaches 0 of cos x, limit h approaches 0 of cos h minus 1 over h, minus limit h approaches 0 sine x, limit h approaches 0 sine h over h. Well, the limit of cos x is just cos x. This one, cos h minus 1 over h, is 0, minus sine x times 1. So we get negative sine x, which, if you go back over to your prediction, is close but not quite. The answer here for the derivative of cos x is actually negative sine x. Now, if you're wondering where that negative comes from, well, it's actually from the trig identity. When we do cos of a plus b, we actually get a negative sign there, and this negative sign follows through all the way along in the proof to give us the negative in the derivative. So it's kind of interesting that way. Now, one thing we can do is apply this idea of higher order derivatives here. So if we had y equal to sine x, then y prime would be equal to cos x. Y double prime would be negative sine x. Y triple prime would be equal to negative cos x. And then the fourth derivative, well, the derivative of cos is negative sine, which gives us negative negative. So just back to positive sine x. So if we notice, it repeats every 4. It's kind of like e to the x. If we have y equals e to the x, the derivative is also e to the x. But here it repeats every 1. For the trig function sine and cos, we have to wait 4 times until it repeats. Now, using these rules, we can actually calculate the other trig functions just using logic. So go ahead and take a guess for tan x. Maybe you think it's maybe cos x or sine x or maybe secant x, some other trig function, but we don't actually have to use the limit definition for it. So when we do the derivative of tan x, we just do the derivative of, well, tan x we know is sine x over cos x. And then rather than doing a limit question, we can treat this like a quotient rule. So low, d high, derivative of sine is cos, less high, d low, derivative of cos is negative sine, over the denominator, squared we go. So we get cos squared x plus sine squared x over cos squared x. Well, we know cos squared x plus sine squared x. That's hopefully an identity you remember. That one is just 1. So we get 1 over cos squared x, which we tend to write as secant squared x. So there's the proof, and the derivative of tan x is secant squared x. Now go ahead and take a guess for the derivative of cotan. Do you think it's maybe cosecant squared x? Maybe related, like the tan is secant, maybe cotan is cosecant. And go ahead and pause the video and try to prove it using the quotient rule. All right, assuming you gave it a try, we do the derivative of cotan x as the derivative of cos x over sine x. Well, low d high less high d low, so sine x, negative sine x, minus cos x over sine x all squared. So I'll give negative sine squared x minus cos squared x over sine squared x. Now if you have negative sine squared x, subtract cos squared x, that's going to give us a negative 1 using our identity. And 1 over sine squared we know is cosecant, so negative cosecant squared x. So we are close if we had guessed cosecant squared, but the answer is actually negative cosecant squared. Negative cosecant squared x. All right, well, let's just keep on going for all the trig functions. All right, let's keep on trucking. Rule number 5, we have the derivative of secant. Maybe it's back to tan, maybe it's tan squared, maybe it's cotan. Take a guess at what the derivative might be, and then go ahead and pause the video and try to prove it using the quotient rule. All right, assuming you gave it a try, derivative of secant will be equal to the derivative of 1 over cos, which is, well, we do the quotient rule. Low d high, derivative of 1 is 0. Less high d low over the denominator squared we go. Well, let's see what we get here. 0 times cos is going to be 0. Negative negative will make positive, so we have sine x over cos squared x. Now to make this look nicer, we'll often write it as sine x over cos x, and then there's another 1 over cos x. So we're just trying to make this look as nice as possible here. Helps us for memorizing. So we'll get tan x, 1 over cos x is secant x, and usually we write it with the secant x first and then the tan x second. So the simplified version for this one is secant x tan x. Secant x tan x. So close, because tan was secant squared, secant is secant tan. I guess there's a bit of a connection there. Let's look at the final rule, try to take a guess. The derivative of cosecant. Well, I'll go ahead and do this. Maybe you can try to race me for it. The derivative of cosecant x is going to be the derivative of 1 over sine x. So low d high, less high d low, over the denominator squared we go. The 0 makes the first term disappear, so we have minus cos x over sine squared x, which we write as minus cos x over sine x times a 1 over sine x. This will be negative cotan x and then cosecant x, which we usually write in the other order as negative cosecant x cotan x. So maybe you beat me on that proof, maybe you didn't. We'll put that up for our rule number 6, negative cosecant x cotan x. Makes a little bit of sense. And we're going to write all of these in a nice grid to help memorize them. So here we have a big, nice chart that has all of our derivatives. So go ahead and make sure you have this copied down nicely in your notes. The derivative of sine x is cos x, and the derivative of cos x is minus sine x. These are on the same row because they go together. The derivative of tan is secant squared, so the derivative of cotan is negative cosecant squared. Again, they're on the same row because they have the same type of pattern. They go together. The tan gives us a square. The cotan also gives us a square. Now for secant, you get secant tan. And so for cosecant, you get cosecant cotan. Again, the same type of pattern. Now, how do you remember if it's negative or positive? Well, if you notice, all of these ones are positive, and all these ones are negative. And what do you notice about the letter that each one of these starts with? Well, it's C. And so all of the ones that start with C have negative derivatives. All the trig functions that start with C have negative derivatives. It's a bit of a quirk, a bit of a weird sort of happenstance. It's not that the c somehow makes it negative. Remember, it's the trig identity that makes it negative, but because they all start with c, which just happened to work out that way, it's a nice little memory trick. If you see a c, then it just has to be a negative derivative, and you should be able to figure out the rest of the pattern for them. So let's go ahead and do some practice. We have the following derivatives. I encourage you to pause the video and give them a try, and then I'm going to go ahead and work through them. All right, so we have the derivative of cos x minus 2 secant x. So this will be equal to negative sine x minus 2 secant x tan x. X cosecant x, well, that will be equal to derivative of the first one and then leave the second alone, plus leave the first one alone, derivative of the second. Make sure you put brackets around that because you can't have a multiplication and a negative side by side. Ooh, the next one looks like an ugly quotient rule, so we get low, d high, less high, d low, over the denominator squared we go. All right, let's try a few more here. So we've got another product rule here. Negative cosecant squared x, x to the 5 minus cosecant x, plus cotan x, 5x to the 4. Negative negative will make a positive, so plus cosecant x cotan x. For this one, remember that we've got to write x to the 1/2 when we have the root. So 1/2 x to the negative 1/2 sine x plus x to the 1/2 cos x. And finally here we have a triple product. So we do the first one. So 1 times e to the x tan x plus the next one, which is just e to the x, plus the last one, which is secant squared x. Let's go ahead and try some challenge problems. So suppose fx is secant x minus 2 cos x. Let's find the equation of the tangent line at pi over 3 and 1. Well, to find the tangent line, you need a slope and a point. To find the slope, you do the derivative, which is secant x tan x plus 2 sine x. And of course, you evaluate this derivative at the point. So pi by 3, which gives us secant pi by 3 tan pi by 3 plus 2 sine pi by 3. So this is a good time to review your unit circle because we need some special values to plug these in. Secant, if we remember, is 1 over cos. Cos of pi by 3 is 1/2, so this is 1 over 1/2. Tan of pi by 3 will be root 3. And then sine of pi by 3 is root 3 over 2. Now the 2's cancel here. And this flips up to give you 2 root 3. So you have 2 root 3 plus a root 3, which is 3 root 3. So finally, of course, this is our point. And this over here is our slope. So we use the point slope formula, y minus y1 equals mx minus x1. And there is our equation of the tangent line. Let's go ahead and show that fx equal to sine x has a horizontal tangent line at pi by 2 and 1 and 3 pi by 2 and negative 1. Well, we should find the derivative, which will be cos x. We could plug in those points into the derivative. So if we plug in pi by 2, we get cos of pi by 2, which is, of course, 0. Horizontal here means slope of 0. So this 0 here definitely checks off the first point. Let's try the next one, f prime of 3 pi by 2. So it'll be cos of 3 pi by 2, which is also 0. So there you go. Both of these have horizontal tangents. So we could say, therefore, horizontal tangents at pi by 2 and 1 and 3 pi by 2 and negative 1. Now, just as something to note here, this should actually be pretty obvious from pre-cal, because if we were to draw the graph of sine x, we would notice that right at the peak of sine x, we have a horizontal tangent line. And right at the valley of sine x, we also have a horizontal tangent line. And these points right here are, of course, pi by 2 and 1, and 3 pi by 2 and negative 1. So you could almost come up with the argument here from pre-calculus, just drawing the graph. But it's nice to see, again, the pre-calculus and the calculus meshing together so nicely. Let's try another one. Suppose fx is equal to e to the x cos x. Let's find the equation of the tangent line at 0, 1. So we find the derivative using the product rule, e to the x cos x plus e to the x negative sine x. And we plug in the value of 0. So e to the 0, cos of 0, e to the 0, negative sine of 0. Now we need to remember that anything raised to the power of 0 is always 1. Cos of 0 is also 1. And sine of 0 is, well, 0. So we get negative 0, which is just 0. And so this gives us 1 plus 0, so 1. This is our slope. This is our point. Y minus y1 equals mx minus x1. Now one more question here. What is the 27th derivative of cos x? Well, I'll give you a second. Go ahead and pause the video and see if you can do 27 derivatives, or maybe find a bit of a shortcut as you begin to work on it. All right, well, we can find f prime as negative sine x, f double prime, negative cos x, f triple prime will be sine x, and then the fourth derivative is back to cos x. And you could keep going, but what that means is after 4 derivatives, you'll be back to cos x. So after 8, you'll be back to cos. After 12, 16, 20. After 24 derivatives, you'll just have cycled through again and again and again. So we can count then and say right here, this would be 25, this would be 26, and this would be 27. So the 27th derivative would be equal to sine x. Let's go ahead and try a couple multiple choice questions. Don't look at your notes for these ones. Which rule is incorrect? All right, well, the derivative of secant is definitely not tan squared. Sine goes to cos. Negative cos will go to negative negative sine, which is true, and tan will go to secant squared. But secant here is supposed to go to secant tan. So rule A is incorrect. Determine the derivative of 7 sine x minus 7x plus 2. Go ahead and pause the video and give it a try. All right, the correct answer is B. The derivative of the 2 is just gone, and then we know the derivative of sine is cos. Now, before we end this video, I want you to think about the derivative of e to the 2x. We know that the derivative of e to the x is just e to the x, but what if there's a 2 there? Is this equal to just e to the 2x again? Is there something about this 2x that changes things? Does the power come down? Is there some kind of rule here? It's not entirely clear. I encourage you to try this question, try this problem, maybe use the definition of the limit. You might have e to the 2x plus h minus e to the 2x. You could probably do some factoring at some point. You could expand some things. You might even end up in a place where you have e to the 2h, which I'll give you a hint. You could write this as e to the h squared. There might even be a difference of squares. Work on it and see what you can come up with. See if you can figure out the derivative of e to the 2x. It might be e to the 2x, or there might be something different about it. And we want to look at this because, well, we want to have other things than just e to the x. We want to have e to the 2x, or maybe even e to the 3x, e to the 4x, and figure out what those derivatives would be. And we'll look at the full explanation of this in the next video, but for right now, try this and see what you come up with. So for homework, you can go ahead and try the questions on page 196, 1 to 19, 21 to 25, 33, and 34. Hopefully you enjoyed this video, and as always, thanks for watching.